This is the video for lessons 7.4 and 7.5, part 1 of exponential growth and decay functions. Now we've been dealing a lot with linear functions, where there's that constant rate of change. However, a lot of things in life don't grow at a linear rate. For example, population, maybe how quickly a virus spreads, the value of something like your car, or even the amount of money in your savings account, those all tend to grow exponentially. When we look at graphs of exponential functions, you're going to see that these tend to grow or shrink very quickly. So what's the difference between linear functions and exponential functions? An exponential function is a function in the form y equals a times b to the power of x, where a can't equal 0, because then nothing is happening, b is greater than 0, and b also can't equal 1. So let's see what happens in these charts. In the first one, our x's are increasing by 1 each time. Our y's are going up by 3. So negative 4 plus 3 is negative 1, negative 1 plus 3 is 2, 2 plus 3 is 5, and so on. So we know that plus 3 each time, for every 1 of x, y increases by 3, that's our slope. And then when x is 0, y is 2, that's our y-intercept. In our exponential function, our x's are still going up by 1 each time, but our y's are not adding the same number each time. In this case, they're being multiplied by the same number. 2 ninths times 3, that would be 6 ninths, which equals 2/3. 2/3 times 3 would be 2, 2 times 3 is 6, and 6 times 3 is 18. So in a linear function, you're adding the same number to get your y's. In an exponential function, you're multiplying that same number to get your next y value. In this one, that times 3, that's the base, that's the power we're talking about. So that's going to be here with the exponent of x. We're still going to look for that starting value, but in an exponential function, that's going out front. So if I identify the parts of an exponential function, we said a, that's that starting value. You might also think of that as the y-intercept still, but it's going out front this time. The b is the base. And that's going to describe how the function grows. So a out front is the starting value, b the base, tells you how quickly it grows. So let's put this to use. We're going to write a function. This is already done for you, but ideally there would probably not be these numbers here and you would go through and check this. But we're looking once again at our x's. It's going up by 1 each time. Now first you would probably check to see if it's linear. So you'd see, are you adding the same number each time to get your y's? 2 plus 2 would be 4, 4 plus 2 is 6, and not 8. So we know we're not adding the same number each time. So now we would go through and check to see if we're multiplying the same number each time. And you can see, yes, we are. We are multiplying by 2 as we go across our chart. So we know what power we are dealing with. Next, we need to figure out, and this is step 2, what that initial starting value is, and that's when your x is 0. So now if we were to write our function rule, we'd have y equals, the initial starting value is 8, the base is 2, that's what you're multiplying by each time, and that 2 would be raised to the power of x. So once again, where x is 0, that goes there, that's the starting value. Take whatever you're multiplying by each time, that's your base, put an x as the exponent. Go ahead and try the guided practice, so pause the video and play when you're ready. Here, as we go across, our x's are going up by 1 each time. Check to see if it's linear. Here we would add 6, But 9 plus 6 does not give us 27, so it is not a linear function. Let's see if we can multiply the same number each time. 3 times 3 would be 9. 9 times 3 is 27. And the pattern seems to stay the same. So now if we're going to put all this together, by equals, the starting value is 27. The base is 3 raised to the power of x. Okay, let's look at the graphs of these. Turn the paper over. Whoops. Okay. And there's really no good way to graph these except by plotting some points. Okay, I know when we did lines, we would plot the intercept and then use the slope to help us out. When we did absolute value functions, the number on the inside would do one thing, a number on the outside would do something else. With these, though, you can quickly plot the intercept, but after that, it's really just plugging in some points and seeing what happens. And you'll probably find you might not even be able to do that many points on these. Okay, just do enough so it fits on your graph. So we're looking at y equals 2 to the power of x. And we're going to make a table of values. I'm going to do -2, -1, 0, 1, and 2. Be my go-to numbers. And in this case, just to see what happens, we're also going to throw 3 in there. Okay, so now these values of x, we are plugging them in for the exponent. So if you need to write it out on the side, go for it. So our first one's going to be 2 to the power of -2. Oh, this is like last lesson on negative exponents. That'd be the same as 1 over 2 squared, which equals 1/4. 2 to the power of -1, that'd be the same thing as 1 over 2. So 2 to the negative first power is 1/2. 2 to the power of 0, well, anything raised to the power of 0 is 1. Next one would be 2 to the first, which is 2. 2 to the second, which is 4. And 2 cubed, which is 8. Okay, and do your best to plot them on the graph. So -2 would be 1/4. -1 is at 1/2. 0, 1. 1, 2. And this is where it really starts to kick in now. 2, 4. And 3, 8. So as you can see, it started out kind of flat, but then quickly started rising. Okay, and you might be a little confused as to how we're going to graph this side. So let's talk about what happens on this side real quick. Okay, keep in mind that if we plugged in a -3 here, it'd be 2 to the -3rd. Okay, which would be 1 over 8. 2 to the -4th would be 1 over 16. 2 to the -5th would be 1 over 32. Okay, and as you keep making these powers more and more negative, okay, you're going to see our fractions are going to get smaller and smaller. But hopefully you notice it's never going to reach a point where it actually gets to 0. Okay, so our numbers, our y values would get smaller and smaller and smaller as we go this way to the left across the graph. But there's no way to get 2 to some power to be 0. So when we graph this, we're going to connect, do our best to connect, and as we graph, we're going to show that it's going to get really close to 0, but it's never going to cross that axis. Okay, for the domain, okay, there's an arrow going this direction, an arrow going that direction. The domain would be all real numbers. Our range, our possible y values, well, we just said it's never going to reach 0, but it looks like it can be anything that's positive, so that would mean that y is greater than 0. And we have a new vocab word, an asymptote. It's a line that a curve approaches but never reaches. Okay, so we said it's getting really, really close to that x-axis, but it's never going to touch it. Okay, so the x-axis in this case is actually our asymptote. Okay, and if we want to write an equation that represents the x-axis, well, that would be y equals 0. All exponential functions are going to have an asymptote. And as you get further along, as you get into algebra 2, there's going to be other types of functions that will also have asymptotes. Okay, so asymptote is a line that a curve approaches but never reaches. Okay, let's see what happens when we change the b. Okay, when we change the base. Okay, we've been looking at things like this. Y equals 1 times 2 to the power of x, where our b was greater than 1. Okay, that's going to be an increasing graph. So that's what's known as exponential growth. However, we can also have something like this, where our b is between 0 and 1. Right now it looks like a decimal. Most of the ones we do, I'll probably make it look like a fraction, okay, but it's between 0 and 1. Okay, that's going to be something that starts off really high, but it drops down quickly. So that's going to be a decreasing graph, which we call exponential decay. Okay, so let's look at these functions here and write some rules. We're going to identify if it's going to be a growth or a decay. Okay, as we go across our x's, we're adding 1 each time. For our y's, well, if we multiply 1/9 times 3, that would be 3/9 or 1/3. 1/3 times 3 is 1, and 1 times 3 is 3. So we are multiplying by 3 across our graph, across our table. Starting value, oops, eraser. Starting value is 1/3. So it's going to be y equals 1/3 times 3 to the power of x. Because of that 3, that means that this is going to be exponential growth because it's greater than 1. In part B, still adding 1 each time. Okay, but now as we're trying to figure out what's going on with our y's, some of you might notice, hey, we're dividing by 4 each time. And you're correct. But the problem is that exponential functions don't deal with division. Okay, we have this base that we keep raising to some power. So we don't want to put something that implies division. However, hopefully we remember that dividing by something is the same thing as multiplying by its reciprocal. So if you're trying to tell me that it's dividing by 4 each time, remember that's really the same thing as multiplying it by a fourth. 4 times a fourth is 1. 1 times a fourth is 1/4. And 1/4 times 1/4 would be 1/16. Figure out your starting value. So it'll be y equals 1 times our base, which is 1/4, raised to the power of x. And we don't really need that number out there, so in this case, it's okay to write it with just the base and the exponent. So y equals 1/4 raised to the power of x. Okay, we are going to write fractions in parentheses just because if we do this, okay, it might be confusing to whoever's looking at your equation. Is this whole thing being raised to the power of x or just that one? So in order to clarify, okay, we are going to write it so that the fraction, that base, is in parentheses. Okay, so that's what happened when we changed the b. Okay, if that b was greater than 1, it was growth. If the b was between 0 and 1, okay, that was a decay. Let's see what happens when we change the a. So for these, on my screen you can see the different colors. Unfortunately on your handout you can't. However, I did label them for you. So actually to make life maybe a little bit better, I'm also going to say that this was equation 1. Okay, this one was equation 2. This one was equation 3. Okay, I'm running out of matching colors, but this one is equation 4, and this one is equation 5. Okay, so we're going to say, how did changing that number out front affect what happened on the graph? Okay, well, right off the bat, hopefully we realize, okay, if that number out front is the starting value, which we also called the y-intercept, that's pretty much what it's going to do. Okay, so if our starting equation was y equals 2 to the x, that's my red one right here. It's in the middle on the top. Okay, since there's no number out front of the base, we can assume it's crossing at 1. Okay, and then it's being multiplied by every power of 2. Okay, if we do 4 times to the power of x. Okay, if our a is greater than 1, first of all, notice 4 is now the intercept. Okay, but we can see that it grows more quickly. Okay, this one took a little bit longer to get up here. This one, okay, notice the value of 2, it's already a lot bigger. Value of 3, a lot bigger. Okay, value of 4, it's not on our graph anymore. Okay, but the y value of graph 2 would be a lot bigger than the value of graph 1. So if a is greater than 1, we're going to call that a vertical shrink. Sorry, I lied. A vertical stretch. Okay, because it's getting bigger more quickly. So it grows more quickly. Okay, we're stretching it up. For my green one, the one all the way to the right on the top, okay, we multiplied it by 1/4 out front, so that definitely shrunk the y-intercept. It's even kind of hard to see there. Okay, but it lowered that y-intercept, and notice it's taking a lot longer to grow. So when we have that a value of a fraction, okay, that's going to be a vertical shrink because it's going to grow more slowly. Okay, I'm going to go down a little bit, so I might lose some of my equations, but okay, that's not bad. If our a is less than -1, like in equation 4, so that's this graph right here, the first one on the bottom. Okay, notice first of all our intercept is now -4 and is flipped upside down. Okay, so it's definitely also going to be a vertical stretch, just like the one on top. Okay, so it's a vertical stretch, is going to change more quickly than before. However, it's also reflected over the x-axis. And finally, the last one, that -1/4, that's that orange one on my screen, the one to the right on the bottom. Okay, so once again, intercept is -1/4. Okay, it's taken a longer time to do stuff. Okay, but also once again, reflected over the axis. So this would be a vertical shrink, and it's reflected over the x-axis. Okay, so if we have something that's bigger than 1 or less than -1, so like a whole number, that's going to stretch it out. Okay, it's going to change more quickly. Okay, if we have that a that's a fraction, whether it's a positive fraction or a negative fraction, that's going to shrink it. It's going to take longer to start growing. Okay, and if we have that negative number out front, whether it's an integer or a fraction, okay, that's going to be something that is reflected over the x-axis. So now, final question on this section: how did the range change for equations number 4 and number 5, where the a was less than 0? Hopefully we see for these that our y in this case is going to be less than 0. Okay, and last example. Some more writing rules for functions, but this time we're using a graph. Okay, so first of all, we want to know if it's growth or decay. Since this one is starting low and getting bigger, that's going to be a growth, okay, which says in your notes. Okay, so we know it's going to be y equals a times b to the x. That's just the general form for exponential functions. Okay, there's one thing that we can quickly tell from the graph, okay, and that's this part right here. It goes through 0, 10. So just like in those tables we did, we looked for where the x was 0, we can tell that that a value is 10. But now the problem is we don't know how much it's growing by yet. But the good news is they also give us another point. They tell us it goes through 1, 12. So what we can do is plug in these coordinates into our x and our y and figure out what that b equals. Okay, so our y is 12. We don't know the b. Our x is 1. Okay, so really that's just 12 equals 10b. And if I want b by itself, I divide both sides by 10. And b would be 12 tenths. We can say 1.2. You can leave it as 6/5, it really doesn't matter. Okay, but we can figure out our b. And now if we plug the information in, we'd have y equals, once again we said the starting value was 10. We just figured out the base raised to the power of x. Okay, so once again, you can quickly tell that starting value, the a, but then you're going to use the other point you're given, plug it in for your x and your y. Okay, solve for that base, and you can figure out what that b equals. Okay, let's do b. This one starts high, goes low. That's going to be a decay. Okay, but we're still going to start out the same way. Y equals a times b to the power of x. We need to first get that important information that the starting value is 8. So we know that goes where our a is. Okay, but now we need to figure out what our b equals. And to do that, we're going to take the other point and plug it in. So the y is 4. The x is 1. So it's 4 equals 8b. Divide by 8. And b equals 1/2. Or b equals 0.5. Which makes sense because we said if the b is between 0 and 1, that's going to be a decay function. Putting it together, we're going to have y equals, starting value is 8, times 1/2 raised to the power of x. Okay, that is it for these notes. Please make sure you write down any questions you have, okay, and make sure to ask in class.